All right, in this video, I'm going to continue to go over 7.4.2, excuse me, the maximum likelihood estimator. Okay, so we'll just studying maximum likelihood function. Right? So the idea is this: we're gonna construct the likelihood function that is defined as the product of PDF evaluate it at each random sample data in a random sample. Okay, and then we're gonna find out. Then that likelihood function gonna be the function of the parameter. Okay, so 7.4.2. So the maximum likelihood estimator. All right, so let me say this MAE. All right, so the likelihood function the L of data here. Data is the population parameter. Okay, I mean unknown parameter. Okay, so this is defined as the product. You know the symbol pi means the product of the terms right there. Okay, so similar to, I mean the sigma of that one is just summation, right? This is a product. Okay, so f of xi and then colon and theta. Okay, so I goes yeah, for example 1 through n if the size of the random sample is n. Okay, so xi is a sample, or the observations. Okay, ith observations. Okay, so what I'm gonna do, since the likelihood function is L of theta, then we're gonna find out the maximum the maximum value of the L. It means that we want to find out value of the data that maximizes L of theta. So this is nothing but finding what the normally the sample the data, there is no the restriction of, I mean there is no domain. Okay, so pretty much we have to find out the relative maximum of, okay, so L of theta. It means that we gotta find the critical value of theta. Okay, and what we learned in K+1. So we saw example textbook 7.9 Bernoulli distribution MLE, and then today we'll see next example, the exponential distribution MLE. Okay, so this is the example. See 7. Give me a second. Now this is example 7.10. Okay, so exponential distribution MLE. Okay, so here x in an exponential distribution, the random value of x denote the distance between successive events from a Poisson process. Okay, with a mean number of events lambda per unit interval. Okay, so the x. So here the random variable. Okay, x be exponentially distributed. Okay, let me just say axp distribute with a parameter lambda. So now we're gonna find out the point estimator of the lambda. Okay, using the MLE. Okay, so the goal is to find the lambda hat. Okay, so definitely, I mean, yeah, definitely lambda hat, which is the point estimator obtained by MLE, can be expressed as the sample statistic, right? So we'll see. Now the in the exponential distribution, the PDF going to be f of x is lambda times e to the negative lambda x. Okay. So what is lambda, by the way? Lambda is number mean number of events, okay, per unit interval. Okay. So now then what? So we construct the now we're going to construct the likelihood function, okay, of random sample of size n. Okay. So L of lambda. So this is the likelihood function. Um, oops, of a random sample of size n. Okay. So that is equal to what? This is going to be lambda times e to the, I mean, f of what? x1, and then colon lambda times f of x2 colon lambda through the what? F of xn colon lambda, is it right? So, I mean, so using the note the symbol the pi, we can say that this is a pi, and the I goes 1 through the n, and then lambda times what? E to the negative lambda times xi. Okay. Okay. So now see, since the lambda is a constant, right? So we that means what? The pi lambda means that the multiply lambda n times. Okay, so we're gonna get lambda to the nth power. Then take it out of the pi, so we got this. Pi I equals 1 through the n, and then e to the negative lambda xi, right? Now, see, pi of e to the negative lambda xi means that multiply e to the negative lambda times xi from I goes, I mean, from I goes 1 to the 1, n, right? So it means that this is equal to lambda to the nth power, okay? And then e to the negative lambda, that's sigma, I goes 1 to the n, okay? And then xi. So now to find out what critical value, right? So to find the critical value, we had we're gonna find the critical value of natural log of L of lambda. Okay, so we're gonna take natural log. Why? Because since the natural log of the L of lambda, so this is the increasing function. Okay, so this is the increasing function, and then what? Let's see. Give me a second. Yes. Okay. So now what excuse me. Yeah, sorry. Okay, so the L of natural log of L of lambda is what? If the critical value of the natural log of L of lambda maximize or minimize, right? We don't know yet. Maximize or minimize this function. That critical value also maximize or minimize the likelihood function L of lambda. Okay, that's why we take a natural log. Okay, and then we find out critical value of natural log L of lambda instead of finding the critical value of L of lambda. Okay, so the other, I mean, the main reason is this. See that here, the take derivative of the L of lambda with respect to lambda is not a little bit complicated, right? So to make the problem easier, we take a natural log, and then we're gonna find out the critical value. Because find the critical value, well, we have to take a derivative, right? So taking derivative this one, a little bit complicated, but when you take a natural log, then it's a little bit easier, or depending on problem, maybe much easier than I mean, finding the derivative going to be much easier, or a little bit easier than defining the derivative of this original function. Okay, so now this is equal to what? The natural log lambda to the nth power e to the negative lambda, and then sigma I goes 1 to the n and xi, right? So now that is equal to, this is equal to natural log n times, and then plus, minus, right, lambda sigma I equals 1 to the n xi, and then what, natural log e, but natural log e is 1. Now this is equal to, so n times natural log of lambda, and then minus lambda, and then sigma I equals 1 to the n xi. So keep in mind this is also that would the actually that can be expressed as what? You know, remember that the sample mean is what? 1 over n times the sigma I equals 1 to the n xi, right? So it means that means what? That can be expressed as what? N times x bar, right? So keep in mind this. Anyway, so we'll find out a derivative of natural log of L of lambda, okay? So d natural log L of lambda with respect to lambda, that's going to be n over lambda, because derivative of natural lambda with respect to lambda is 1 of lambda, okay? And then minus sigma, right? Minus sigma I equals 1 to the n xi. I told you this is equal to what? That is equal to n times x bar, right? Okay. So now we set this one. Okay, we solve what? To find out the natural the critical value, we solve the n times x bar equals 0. Okay. Then what? Lambda gonna be what? Solving this one, then we're gonna get 1 over x bar. 1 over x bar. Okay. So now the MLE of lambda gonna be, so now we can say that lambda hat, which is the MLE, the maximum likelihood estimator of lambda, is equal to 1 over x bar. So that is the same as the moment estimator. So actually we figured out what the moment estimator of the exponential of the lambda in the exponential distribution. Okay, so that was also 1 over x bar. Okay, so the method of maximum likelihood can be used in a situation that have several unknown parameters, say theta 1, theta 2 through theta k, to estimate. Okay, and then in such a case, what that maximum likelihood function gonna be the what function with a multivariable, right? That we have to apply the partial derivative. Okay, so the keep in mind, but that's I think the beyond of this syllabus, so I'm not gonna cover that one. All right, so I mean that's why so the maximum likelihood is a really powerful, popular method for finding point estimator. Okay. So in the next video, I'm going to cover, we see another example. We're gonna find MLE or mu and sigma square in the normal distribution. Okay, so a lot of computations involved. So I'll stop here, and then I'm gonna see that example next time. Okay.